All right, ladies and gentlemen, this class recording has started. So, yesterday we began our discussion of average atomic mass, and our discussion began with isotopes. So, compare, contrast atoms that are isotopes of each other. If we compare them, what do they have similar to atoms that are isotopes? Austin, go ahead. Same number of protons, but a different mass number, which then also requires that they have a different number of neutrons, right? So isotopes, same protons, different neutrons. Maybe. There we go. Okay. Isotopes, same protons, different neutrons, okay? Then we shifted our discussion to the difference between mass number and atomic mass. Mass number and atomic mass. I want you to take 30 seconds. I want you to talk to the person next to you and discuss the differences between mass number and atomic mass. Go. The atomic mass is something that I would have to give to you. That's not something you would be able just to, like, you would have to look it up on a chart or something like that, okay? It's not really something that you can find, like, it's not on the periodic table if that's what you're asking. It's definitely something I would have to give to you, okay? Same thing with mass number, too. All right. Mass number. What does the mass number tell us? What does the mass number tell us? Liam, go ahead. Sum of the protons and the neutrons. So I said that mass number is always going to be what? That's a general question. What form of a number will the mass number be? It's always going to be a whole number or an integer because it's a counting thing, right? But atomic mass is what? What is the atomic mass? Augustine, go ahead.
It tells the size of an atom relative to a element.
It tells the size of an atom relative to, let's go with a standard, right? Carbon-12 is that standard. And you brought up the idea of relative, right? And we kind of discussed yesterday, and we also discussed it a lot in your Bean lab, when we're setting up a relative scale, what are we doing? Do you want somebody else to take it?
Yeah.
Polly, what does relative scale do for us? It compares things,
okay, I would've said
right? So in this case, we are comparing, like you said, right, Augustine, we are comparing the mass of atoms, right? But when we're comparing things, we have to compare them to a standard. And that standard is what?
Carbon-12.
Carbon-12. And we learned yesterday that carbon-12 has 6 protons, 6 neutrons, 6 electrons, right? So the atomic mass compares the size of that atom to carbon-12. All right? But we also saw that it isn't a nice even jump, right? That when we looked at the size of, let's say, magnesium-24, which we saw yesterday had 12 protons, 12 neutrons, 12 electrons, it's not exactly twice as big as carbon-12 because we assign carbon-12 what value? For the comparison sake. What value does carbon-12 get? 12. Exactly. Right? So here's carbon-12. Here's its atomic mass. Exactly 12. Which kind of makes sense because it has 6 protons and 6 neutrons, so that gets us to 12. We know that electrons are really, really small, and they don't really kind of add much mass to the atom at all. Right? So most of the mass comes from protons and neutrons. Right? But then when we go to something that has twice as many protons and twice as many neutrons, it's not exactly twice as big. It's just how it is, okay? Protons, neutrons, not exactly the same all the time, okay? Good there. But then we also got into the discussion that while atomic mass is a comparison of atoms and the size of atoms to carbon-12, when we look on the periodic table, right, we looked at magnesium, and the atomic mass listed for magnesium is 24.31, which isn't any of these values listed on the table for magnesium, right? Because we said that value on the periodic table is a what? It's an average, but it's not a straight average, right? Because, go ahead, Nate. It's based not only on how big each element is, but also how often it shows up, right? So we have to look at the size of each atom, or the atomic mass of each atom, but then what percentage of atoms are that isotope. And that gets us the average atomic mass, right? Yikes, there we go. Okay. So, I think this is where we left off yesterday, right? That not all isotopes occur naturally in the same proportions. Some isotopes occur more often than others. The average atomic mass takes into account that distribution. And how much does each one individually weigh? Okay? Good? Let's take a look at some oversimplifications of this idea, but it illustrates what we're talking about. All right. On the left, and you guys have these pictures on the back page, I believe, yes? Okay. All right. On the left is a sample of an element called bromine. All right? So, first, what can you tell me about the element bromine? There's two things you should be able to tell me about the element bromine right now if I asked you. Liam. It has 35 protons and 35 electrons. Liam, and you know that because its atomic number is 35. Good. Okay. But what we find out is that there are two isotopes of bromine, right? And Austin, you told us earlier that isotopes are atoms that have the same number of protons, but different number of neutrons, right? So, the two isotopes of bromine, one is bromine 79 and one is bromine 81. Okay? Now, we could go through and we could figure out how many neutrons each one of those has, but we've done enough of that right now, so let's talk about how it contributes to our discussion here. If we wanted to figure out the average mass number of bromine, what would we do? Liam? Add up both mass numbers of all the atoms that we got and divide by the number of atoms, right? That's kind of difficult because there's lots of atoms in a sample. But let's say we took a random sample of bromine and we found 8 atoms, okay? You couldn't find a sample that only has 8 atoms in it. It'd be way too small, but let's say we did, okay? And of those 8 atoms, 4 of them were bromine 79, okay? Which has 35 protons, and if I do this math in my head correctly, has how many neutrons? Anybody? I just want to make, I told you I wouldn't make you do this, so it has 44 neutrons, okay? If I did that math in my head correctly, I think I did, but okay. So, bromine 79 has 35 protons, but 44 neutrons. 4 of those bromine atoms are bromine 81. Bromine 81 still has 35 protons, but it now has 46 neutrons. Yes? Right? Okay. If we wanted to find the average of these 8, what do? Well, we take up the mass numbers of all those, add them together, right? Divide by 8 atoms, and we find out that the average atomic mass of those values, right? I guess I should say average mass number, because that's actually not the atomic mass, it's the mass number. Even though it's listed as atomic mass, right? Let's not be fooled, okay? The average mass number of bromine is 80. Okay? Now, why is that important? Actually, you know what? I'm going to hold on to that question. Hold on. Okay? All right. On the right, there is a sample of chlorine gas. Okay? So, again, two things you should be able to tell me about chlorine atoms right now. Eric, go ahead. 17 protons, 17 electrons, because that's the atomic number of chlorine, okay? There are two different isotopes of chlorine, chlorine 35 and chlorine 37. Chlorine 35 will have 18 neutrons. Chlorine 37 will have 20 neutrons. But, unlike the bromine sample, if we took 8 random atoms of chlorine, we find that there are only 2 that are chlorine 37, and the rest of them are all chlorine 35. Okay? Why? It's just how we find it out there in nature, right? There's no real reason. Well, I guess we don't really know the reason behind it. We just know that it is. When we sample chlorine, we find out that 3/4 of them are chlorine 35, but only 1/4 of them are chlorine 37. Okay? So we add up all of them, and we get an average of 35.5. Okay? Does that make sense? Yeah? So, the bromine, the average was right in the middle of the two isotopes, right? Bromine 79, bromine 81, the average was 80. Here, with chlorine, the average is not right in the middle. Chlorine 35, chlorine 37, the average isn't 36, it's 35.5. Why? How are they distributed in bromine? Nice and even, right? So the average is right in the middle. But are they distributed, are the isotopes distributed evenly in chlorine? No. They are not. So the average creeps closer to the number that there's more of, right? That's how averages work. Does that make sense? Yeah. Right? I think we talked about that yesterday on like, you know, if you took 5 tests in a class and you got 4 80s and a 90, actually let's go 4 90s and an 80, right? Is your average 85 for those tests?
No.
No, it's closer to 90 because you got more 90s than you did 80s, right? Does that make sense? Yeah. Okay. Why is this important? Well, this is how we calculate the average atomic mass. This little formula here shows us how much each isotope contributes to the overall average. So first, you need to know the atomic masses of each individual isotope. Okay? And Donna, you mentioned it a little bit before when we were talking. Okay? I have to give you this value. I have to give you the atomic mass for each individual isotope. Like those tables that are on the front side of your outline, the table of the carbons and the table of the magnesiums. That's information either I have to give to you or you have to look up, right? It's just not something you would know or be able to figure out. That's information that we have to give to you, okay? But then you're going to multiply it by a fraction. First, the fact that that fraction is over 100 might tip off what that fraction is getting at, right? Fractions over 100 are a way for us to represent what? Percentages, right? If I tell you something is 20% of a sample, that's 20 over 100, right? So this fraction right here, abundance over 100, is taking into account what percentage does that isotope show up. Okay? That will give you the contribution of that isotope to the overall average. All right? Good? Let's try it. All right. What we do is perform this calculation for all of the isotopes and add them up. When we add up all the contributions, that will give us the average atomic mass. So you're going to do this little calculation for all of the isotopes of an atom, or sorry, I should say of an element. You'll get the contribution of each one, and then once you know each one's contribution to the average, you add them all up, and that gives you the average. Okay? Augustine, go ahead.
Wait, what makes up the abundance?
So the fact that it's over 100, right, means that it's kind of showing us what? Any fractions over 100 are basically like what? Percentages, right? So the abundance is what percent of the atoms in a sample are that isotope. Does that make sense? So if we go back,
So back to like the chlorine where it's like 235 and the rest like 37.
Other way around, okay? So the contribution, sorry, the abundance of chlorine 35 would be what? 6 out of the 8 of them are 35, so it would be, what would be its abundance?
Would I put that in a percent?
Yep, you put that in a percent, right?
I'm not that good.
6 out of 8, man, come on.
6 out of 8, okay, let me break this down. So, 100, that would be 75%.
75%, right? So if we were doing this calculation for chlorine 35, we would put 75 over 100.
Okay.
But then when we did it for chlorine 37, right?
It would be 2 out of 8, so 25 over 100.
Right? Because 75 and 25. Yeah. All right. Good there? Okay, so let's do this. Okay? Here, and I believe you guys have these numbers, right? Okay? Here is actual data for chlorine. Okay? That picture we saw before was just kind of a representation. Here's some actual data. All right? So, let's calculate the average atomic mass for chlorine. 2 isotopes, chlorine 35, chlorine 37. We have to do a calculation for each of them. The formula that you use is right above there. So, we're going to take the first one for chlorine 35, and we are going to take its atomic mass, which I have given you right here. The atomic mass of chlorine is not 35. It's close to 35, but it's not exactly 35, right? And then we're going to multiply it by abundance over 100, right? Whether you write it that way or whether you understand that I just turned it into a decimal, yes, okay? I don't care if it makes, math-wise, whatever makes sense to you. All right, so you can write it as 75.53 over 100, or you can just turn it straight into a decimal like this, okay? And you plug that into your calculator, and you should get somewhere around 26.41. Good there? Then you'd have to do the same calculation for the next isotope, right? Chlorine 37. You take its atomic mass, which is 36.9779, 0. Here's the abundance. So now you put 24.47 over 100, or you can just turn it straight into a decimal like this, and you get this value. We said these two values on the side are called the what? If you look up a little bit earlier on your outline, what is the answer to this little calculation labeled as? Now, these aren't the averages, these are the what? These are the contributions to the average. What do you do with these numbers? Well, what does it say right above there? I mean, add them all up, right? So you add them all up, and you get this. 35.46. I am not following sig-dig rules here, so just don't freak out too much. Okay? So, did we get it right? How do we know that? How can we check our answer? Go to the periodic table, right? Go to the periodic table and find chlorine. And the average atomic mass listed for chlorine is 0.45. Rounding, right? You know, depending on how you round sig-dig wise and stuff like that. There we go. Does that make sense? Okay. So, question. If I just look on the periodic table, all right, let's do this. Find magnesium on the periodic table. We looked at it yesterday, yes?
Good.
And the average atomic mass is 24.31. If I said to you, which magnesium isotope is the one that shows up most often, what would you probably tell me, or what's your best guess? I mean, let's go with magnesium. So, magnesium, right? The average atomic mass is 24.31. Jillian, which one would you probably guess? Magnesium 24. Jillian, why is that your guess? It's the closest to 24.31. Usually, the average is closest to the one that's most often shows up. And if we look back on the front side of your paper, and you look at the list of magnesium isotopes, magnesium 24 is the one that has the highest percentage. So that holds true, right? Look at oxygen on your periodic table. Okay? Oxygen is labeled as 16.0. What is that telling you about the isotopes of oxygen? Oh, sorry if I'm making you dizzy, right? What is that telling you about oxygen? Augustine, go. In fact, there are a couple, okay, but what's the one that's most common?
16.
Oxygen 16, because the average is pretty much 16, right? Look at carbon. I should have given you carbon as the example on that one, right? Okay. So, what's the average atomic mass of carbon? 12.01. That tells you that most of the carbon atoms that are out there are which carbon isotope?
12.
Carbon 12. All right. Does that make sense? Okay. All right. Let's wrap this up here. Not for the day, just this idea. Okay. The sheet I gave you today. Okay. Honors Physical Science problem set, average atomic mass calculations. Let's take a look at the first one. All right. So it says, naturally occurring copper consists of two isotopes. Based on the information listed below, calculate the average atomic mass of copper. Now, just as a guess, sort of like, are we on the right track, so we can check at the end, right? The average is probably going to be closest to what? The average here is probably going to be closest to what? 63, right? Because that's the most abundant isotope that's out there. Does that make sense, Don? Okay. I thought you said 62. Sorry. I misunderstood you. That's why I gave you that look. I apologize. So. All right, so to figure out if we're right, again, on those fractions, right, if you just want to turn them straight into decimals of 0.691 or 0.309, that's perfectly fine. If you understand it, saves you another step, whatever, I'm okay with that. So when I did all the calculations, did what I was supposed to do, I got 63.548. Am I right? How do you know? Go to the periodic table, right? Check out what the average atomic mass for copper is. Oh, I should turn the camera on. 63.55. I think we did pretty well. All right. Good? Okay. All right, so for homework tonight, put back here. So a couple things, right? First, there are a couple of problems out of the book. These talk about average atomic mass in general, okay? A couple of things from chapter 5. And then finish up that sheet. Some of them are calculations. Some of them are questions just related to the averages and the weighted averages, right? Remember, the answers to that sheet you can find down at the bottom where it says attachments, okay? Tomorrow, we'll start getting into how do we count these atoms, how do we use these numbers to count these atoms, and we'll go from there. You guys still have about 13 minutes left. If you want to work on those now, feel free to do so, okay?